Oh, okay. Okay, good. I will put that on. Okay. So, good morning, Mahela. How are you today?
Good, how are you?
Good, thank you. I don't want you to feel like you're remote, you might be in your bunny slippers. It's that have to be part of the class, right? Okay, we are about to start. We're missing one person today, but imagine Ashton will be back in here in a second. Okay. So you should have received from me yesterday your graded assignment. And at the top of when you look at either the PDF or the source file, right at the top, your name is there and I tell you how you did overall. And then in the document itself, I have specific comments on the way you answered a problem, try to be constructive. I also, in some cases, gave you some illustrations of how you might modify your tech, sort of a live version of Overleaf. I am, and so you wouldn't necessarily know that, but over time, if you start to incorporate it, you'll find yourself liking some of the suggestions I've made. In particular, with certain types of statements in mathematics, aligning it vertically, it makes it easier to read. Whereas if you tend to have it in this tapeworm, snaky tapeworm style, it's a lot harder to read. So using a visual vertical display, this is called alignment. It's easier to read. And so in yours, Josh, I did some things using the align command. And once you see it once, you pick it up immediately. Actually, I did it in everybody's that I saw. So, but as for the quality, there was substantial improvements in everybody. So my advice is come to office hours a couple of times a week if you can. It'll make a huge difference in your efficiency and the level at which you understand things. And that'll help minimize the frustration part that I know is there. But, and if you have problems with tech that goes beyond me, the tech staff here for the college, they can help you out immediately so that you're not without any resource on that. Okay, today I want to talk about a material that's related to assignment 3. So I'm going to go between several forms. I'm going to take a look at assignment 3. I'm going to take a look at the material that's related to carrying that out. And then as always, the Sketchpad construction side of it. In this particular homework assignment, I've asked you to create a Sketchpad file illustrating a particular phenomenon. Let's see if I call this up right here. So for example, in problem 1, I want you to build a Sketchpad model of this problem. So you'll be sending me the Sketchpad file, okay, and it'll be assignment 3, problem 1 in your name, okay, so something like that. And then I look to see that you do it right. Okay, this will help you build this more as a tool as you go through the class. And on exams, I'm going to be asking you to build Sketchpad models. So the expectation is you're going to do it gradually here from this point forward. So what I find in practice is that when a student can build a Sketchpad model, they usually almost always do better on the problem. They have a better understanding of it. And so it becomes a real tool. And that's what tools are. They're supposed to be helping us out. Okay, so now today I want to talk about the concept of when lines are parallel and how we understand that. And it's a classical topic about how we know when two lines are parallel. And our way of probing this is by using something we refer to as a transversal. So the word transverse means to go across, okay? So the idea of a transversal to two lines is a line that crosses both lines. So it's a pretty simple idea. But that crossing creates natural pairs of angles. And the term that's given to them are alternate interior angles. So I'm going to give you an illustration of that in a second. Okay. So the main theorem on when lines are parallel has to do with this idea of a transversal. And the way it's stated here, it says, let n be a transversal of two lines, L and M. Okay, so it's a third line that crosses over the other two. Then a pair of alternate interior angles that's determined by n. There'll actually be two pairs. That pair is equal in measure if and only if the lines are parallel. Okay, so that's the logical relationship between the two concepts. So we know what we mean by lines being parallel. In fact, on assignment 1, I had you looking at that in Descartes' plane. Okay, but the organic definition is the lines don't intersect. Okay? So that idea is the same as saying that a pair of alternate interior angles have equal measure. And it doesn't matter which transversal you use. If you use one, and it's true for all of them. Okay. So, so by nature, this is what we call a biconditional statement. Statement P, if and only if statement Q. So this is your Math 287 approach. Okay. So the forward direction is, suppose we have a pair of alternate interior angles that are equal. That's the P part. Then we have to prove the lines don't intersect. That's the Q part. The converse is if you start with the lines being parallel, then you have to prove a pair of alternate interior angles is equal in measure. They're equal in measure. Okay, so the forward direction is a consequence of what we call the exterior angle theorem. Okay, I have a worksheet on this in the course notes. And it's a very elementary, I want grade 9 level type worksheet. You could do it in a grade 9 course. Okay. Doesn't mean it's not challenging. It's just that you could do that in that curriculum very naturally. So I'm going to talk about that. That exterior angle theorem itself, it's a consequence of the SAS axiom, something we've been working with rather deliberately on the second assignment, as well as on the current assignment. So there it is again, SAS. The converse direction, that's Q implies P. This is a consequence of two things. Angle construction, that's the second of the angle measure axiom, something we just recently used, and the parallel postulate, something we studied in assignment 1. Okay, so we're going to pick those up and use them to prove the converse. Okay. Now my approach is going to be one that is perhaps a little, I don't know if foreign is the right word, but it may not be an approach you've done very much. Okay. And I'm going to ask you to say, suppose you knew that the forward direction was true. Okay, suppose you knew that. Could you prove the converse direction? So that's the, if you read the forward direction is a statement about anytime I have a transversal for two lines. So it's a universal statement about all possible transversals of two lines. And it says, whenever I have such a transverse, whenever I have a transversal, if the alternate interior angle pairs are equal in measure, then the lines are parallel. The converse is saying, if I had two lines being parallel, then there must be a transversal with this equal measure property. So the strategy here is we're gonna do this. We're gonna say suppose we know that P implies Q is true. Okay. Now we're going to try to prove Q implies P. Okay, so let's go back to Sketchpad and draw a picture of this. So I'm going to draw a pair of lines, and I'm going to make them appear to look parallel. Now I could force them to look parallel using Sketchpad, but I want to eyeball it for a moment. Okay, so I start drawing a second one. That looks pretty parallel there. Okay, now, so question to all of us, how do I draw a transversal to those two lines? So this guy, just for the L of it, this will be L and this will be M. Yeah, just draw any line that intersects both of them. What we do know is when two lines that aren't parallel intersect in exactly one point. So I want a line that intersects the L line once and it intersects the M line once. So pretty much I can do that just by doing that. There's a transversal. And I'm going to label that N. Okay, now construct the intersection points of L with N, intersection point, and then construct the intersection point of M with N. If it'd be useful to label those points, so I'll label the first one A and the second one B. Why? Just because I can, and today's Monday. So in that picture, there are two pairs of what we call alternate interior angles. Now I explain what these are in the course notes. So what do I mean by alternate and what do I mean by interior? Well, the word alternate has to do with one of the angles is on one side of N and the other angle is on the other side. Interior has to do with the angle falling in the region between the L and M line. So right up here, if I grab my marker tool and click and drag from the vertex, I'll produce one angle. Click and drag through the vertex, I get the other one. That's a pair of alternate interior angles. But there's a second pair. Okay. And the second pair is right here. So there are two pairs there. Okay. Now, what the theorem is saying is that if either pair are equal in measure, then the lines are parallel. Conversely, if the lines are parallel, then each of those pairs are equal in measure as a pair. Okay. Okay, so in this particular example, if I label this one alpha up here, just to give it a name, alpha, and I label this one down here, you guessed it, beta. Oops. Beta. We can make those measurements and let's call up their measurements. So the measure of alpha and the measure of beta. Now, I said the lines are parallel. If the lines are parallel, then okay, those angles have to be equal. So that's our assumption. If suppose the lines are parallel. So that's the Q part here. Okay. So back here in the notes here, going through the lecture notes, we're saying so Q in this case, Q statement is line L is parallel to line M. Okay. So we're starting with that as our assumption. Okay. That's what we're starting as, assuming that that's true. Okay. So in the sketchpad figure, boy, it looks pretty close, doesn't it? But it's pretty clear it's not. And one way you could see empirically, if those lines intersect, they intersect so far away from this screen that we can't see it, right? But if we think in terms of the parallel postulate, what do we know? We know that through the point A, there is exactly one line that is parallel to the M line, right? So in the sketchpad construction, if you click on point and line, it'll allow you to construct a parallel. That's the postulate. So I do that. And what I see in the picture there is, oh yeah, even though I tried to eyeball it, I was slightly off because I had too much coffee or something. You know, I had the jitters. Okay. So if I were to grab that and try to fit it on top of that line A, I can sort of see it. I can get it. Yes.
So the other day we were talking about the methods in the background that Sketchpad uses to construct these. Does it use like a perpendicular bisector or a perpendicular bisector to construct that? Or?
Well, no, not this. No, it really is working with Descartes' model. Okay. So it's doing a lot of coordinate algebra. It just doesn't force you to look at it. Okay, so this is the starting point for the argument. I'm going to prove this by contradiction. Okay, so when you prove an implication by contradiction, what does that mean? Okay, so we're going to go through that thought process. So we will prove Q implies P by contradiction. So the general question is, what does it mean to take that approach? What are you assuming when you're going to proceed by contradiction? Well, the basic starting point is I'm assuming the implication is false. Okay, so this means that we assume that Q implies P is false. So that brings you to the next question. When is an implication false? Just at the level of logic.
P is true and Q is false.
When the hypothesis is true and the conclusion is false.
Mm-hmm.
So this means we're assuming that Q is true and P is false because we're doing the converse direction. I know what you meant to say.
Okay.
Yeah, the spirit of what you said was completely right. Okay, so this means we This means we assume Q false.
We assume, because we're doing commas, we assume Q is true.
But the implication that we're proving is Q implies P.
Yeah, so we assume that Q is true.
We
and
assume that Q is,
false.
we assume that Q is true, good. That's my dyslexia. Okay, great,
And P is false.
and
right?
P is false,
Okay,
good. Hey, think about this. You could be falling asleep here, right?
good. Keeping me on my toes, for
Right,
sure.
that's exactly right. Okay, so to say that Q is true means we're maintaining the truth of the lines being parallel. Okay. To say that P is false, what is that we're saying that either pair of alternate interior angles are not equal in measure. Okay, so to say this explicitly, so L is parallel to M, and a pair of alternate interior angles are not equal in measure. Okay, pair of alternate interior angles.
When we're doing a proof by contradiction, do we have to write out that we're assuming that the consequent is false, or is that just assumed when we write proof by contradiction?
Well, okay, let me finish this sentence, and then I'm going to answer your question. Okay, you remember I post these every day up on Moodle, so you can always go to this source file and download it. And this gives you some daily practice with LaTeX. So when we're going to prove, when we assume that Q implies P is false, this means we assume Q is true and P is false. So L is parallel to M, and a pair of alternate interior angles that is created by a transversal are not equal in measure. Okay, now ask your question.
So when we are doing a proof by contradiction, do we have to explicitly state that we're assuming that Q is true and P is false? Or is that just assumed because we said we're going to do a proof by contradiction?
The answer is no. The long answer is, if you're sophisticated and you say we're going to argue by contradiction, and you were an expert, you would say you might even leave that out, because you're expecting the reader to know that you've assumed the hypothesis is true, and at the same time the conclusion is false. But I was writing here as a teacher, the people that are thinking their way through it. And so I'm being a little generous in saying, what is it again that I've assumed? And so I'm saying, oh yeah, you've assumed this and that. Now, if you were to write that, would that be over the top? No, not if you write well. Okay. The critical thing is that you recognize that, oh, when I say I'm going to prove it by contradiction, I'm assuming the implication is false, and I better know what I mean by that. Okay. So I'm for clarity, right? Sometimes an extra sentence, well written, is well received. So that, all right, so let's go back to the sketchpad picture and give an illustration of what we've written here so far. So we have this original pair of angles. So my lines L and M are parallel. So that's what we've assumed. And at the same time, we've assumed, say, alpha doesn't equal beta. So that's what we've assumed. So in the figure on Sketchpad, we've assumed L is parallel to M and alpha doesn't equal beta. Okay. So hold that thought for a second. In the figure, in the sketchpad figure, we have L parallel to M, and alpha does not equal so that's what we said. Okay. Well, we have angle measure axioms. There's 4 of them. And one of them deals with angle construction. This is something that was in problem 1 of the second assignment. And it says that if you pick a side of your line, there's exactly one ray from the A point moving in one of the directions. Okay, say let's go to the left. So that the angle that's formed with the end line, okay, so I'll draw that ray here. So here it is. There's exactly one ray I can construct. So there it is. I'll exaggerate here a little bit so it's easier to see. So that the angle that's formed by that ray, the point A and the point B, right? So if I exaggerate here, I'll put a point on this other line, so I'll call it C. So there's exactly one ray AC on that side, so that the angle CAB equals beta. That's what the angle construction axiom says. So we could do that on either side, but so we picked a side. Okay. So using the angle construction axiom, let's write that in. Using the angle construction axiom, and one of the sides of the end line, because it's a sidedness thing, and one of the sides of the line, the half planes, one of the half planes on the of the line N. Okay. There is a unique ray, one and only one. There's a unique ray beginning at A, right? So it's, you write it this way in my notation for rays, AC, such that the measure of the angle CAB, okay, equals and we did that in the very first step of problem 1 in the recent assignment. So I'm going to compile that just so we can read it. Although you get good reading Sketchpad source, get LaTeX source after a while. So using the angle construction axiom and one of the sides of the line N is a unique ray such that CAB equals beta. So in my picture, here it is. So that this angle here, that's the same as beta. Okay. Now, go back to the starting point. The starting point was, suppose I knew the forward direction was true. Suppose I had proven it already. Suppose I was smart enough to be able to prove the forward direction. Okay, let's go back and read the forward direction here. The forward direction The forward direction is that if a pair of alternate interior angles are equal, then the lines are parallel. Right? So that's a universal statement about all possible pairs of alternate interior angles. It says if one pair is equal, then the lines are parallel. Can I use that to complete the argument? So on the picture here, let's take a look at it. I constructed a ray, but constructing the ray is the same as constructing a line, because a ray requires 2 points, a beginning point and a second point. So that angle that I constructed, CAB, also is building a line, the line through C and A. And so what have we proven? What do we have an example of here? We have a line where a pair of alternate interior angles are equal. What does that say about the highlighted line with the M line? What does the forward direction say? That if I have that picture, what has to be true about the highlighted line and the line M? So go back to the beginning point. Let's imagine I've assumed P implies Q is true already. What does P implies Q being true mean? So that's the this is the part that's where the learning curve is here. So logically, I've already been able to prove that. And I put it aside, okay? What must I be able to conclude based on that?
Like two interior
Yep,
angles are equal, then the lines are parallel.
right. So that implies the line through C and A by the forward direction. The line through C and A has to be parallel to the line M. So that's what that means, because the moment I produce an equal alternate interior pair, the two lines that are created that way have to be parallel, because that's what the forward direction says. Okay, so I'm going to write that down. Okay. So I would say this. Hence, by the forward direction, P implies Q, the line that passes through A and C has to be parallel to the line. So this depends on my sketchpad picture. So for example, if I asked you to create a model, you'd have the model that would support that. For you techsperts out there, there is a way to create PRN files or PDF files that you can include as graphics. And I'll show you how to do that if you want to know. It's not hard. So you could have a figure incorporated into your LaTeX file that would display exactly what you wrote. In fact, if you look in my course notes and my worksheets, you see that. That's how I'm doing it. Okay, so hence by the forward direction, the line through A and C is parallel to the line through M. Okay, at this point, I sense there's going to be a contradiction. What's the contradiction at this point? Remember at the start, I said there are two ideas that are involved in the converse. One is the angle construction axiom, and the other is the parallel postulate.
You can only have one.
Go ahead, speak up.
You can only have one parallel line to your original.
You can have only one parallel line through A that's parallel to M. So what does that tell you? That line had better be L, because by assumption, you assumed L is parallel to M. So the uniqueness of the parallel, that's the parallel postulate, says, oh, that AC line, that has to be L. Otherwise, I've got a contradiction. Okay, there's only one parallel, and then there's two parallels. Right, so that's what's going on here. Okay, so I can say, I'll write that in here. Okay. By the parallel postulate, I can spell postulate. There is only one line through THRU, one line through A that is parallel. This means that the line through A and C that we just constructed has to be L, otherwise we have a contradiction. Otherwise, we have two lines. Okay, and that's a contradiction. And that completes the converse direction. So what might make this argument feel a little uneasy in you psychologically, it depended on you willing to suspend your belief that I know the forward direction is true. And since we're all modest by nature, we're not that narcissistic. You said, well, I know why the forward direction is true. Right, immediately. We're saying, okay, I'm not quite sure. But suppose my joke, suppose I was smart enough to know the forward direction was true. Could I use it then as a tool? Because it's logically independent of the converse. And the answer is yeah. It says, I know that I can create a second line where an alternate interior pair, where the alpha and beta are the same, so to speak, the two betas, if you will. Well, that forces there to be two parallels through A to the M line. Well, that can't be. So they must be the same line. Okay, so getting back to the theme for today, whenever I have a transversal of two lines, the lines being parallel is equivalent to a pair of alternate interior angles cut out by a transversal being equal. This is sometimes called AIA. Okay. Now, in your course notes, I have a nice discussion of that, so you can read in the course notes as well. Okay, I want to go back to the forward direction because at the end of the day, why is the forward direction true? And the forward direction depends on something called the exterior angle theorem. Now, in the course notes, I created a little worksheet, like a group worksheet that you could give a class that would explain why you know it's true. So I'm going to give you a visual model of it right now so you can see what actually has to be established to prove P implies Q. Oh, by the way, a special case of theorem 2 is the case where two lines are perpendicular to the same line. Suppose L and N are both perpendicular to N. Well, then I've got an equal pair of alternate interior angles because those pairs are 90, right? Sometimes this case is proved independently, but it's a natural corollary of this main result. And that has to do with what's going on in problem 1 in the worksheet, in the recent assignment. Okay, let's go back to Sketchpad, and I want you to call up a new sketch and construct a triangle. And I'll label A, B, and C like so. Also construct the ray that starts at B and passes through A. So you have that picture. And I'm going to, the angle at vertex A, I'm going to label it alpha. Come on. Label it alpha. And I'll call the one at B beta, and the other one I'll call gamma. Alpha, beta, and gamma. Now, at vertex A, there is a natural supplementary angle to the angle at vertex A. So the word supplement means it's the angle that's formed to add to 180 with A, right? They would call that a supplement or a linear pair. That's your fourth angle axiom. So in the picture, it would be right here. Okay, that's this angle. Okay, I'm going to call it alpha prime. Alpha prime. And what I know about alpha prime and alpha is that they add up to 180. Okay. Now, in the course notes, that angle alpha prime is referred to as an exterior angle of the triangle. Okay, so it's not enclosed by the triangle, it's outside of it. And this is called the exterior angle at vertex A. Okay, so alpha prime is called the exterior angle at vertex A. So the exterior angle theorem says the following, that the measure of alpha prime is greater than the measure of gamma as well as beta. So whatever the measures of gamma and beta are, they're less. They're each less than the measure of alpha prime. That's the exterior angle. Yeah.
Could you say that alpha prime is equal to beta plus gamma?
You can, if you accept the parallel postulate.
Why would you need to accept the parallel postulate?
Because the most famous theorem from basic triangle geometry is that the sum of the angles of a triangle add up to 180. And the standard proof of this fact is to consider the line through C that's parallel to AB. By the parallel postulate, there's only one such line. Okay. Now, if you're a grade school teacher, the grade school teacher says the AC line is a transversal. Right, Ashton? Right? So what is that telling you about alpha? It's telling you that this guy up here is alpha by what we just proved. If we assume it's if and only if, right? Likewise, the BC line is a transversal, which says that this beta down here has to be the same as the beta up here. But those three angles clearly add up to 180. So it depended on knowing that there was a unique parallel that goes through the C point to the AB side. So this is something that's right at the foundation of why we know it. We know that because of this, not independently. In fact, the assumption that the angles of every possible triangle add up to 180, that fact, if you know that's true for all triangles, then the parallel postulate holds. Conversely, if the parallel postulate holds, that's true. So that's at the heart. And historically, that's interesting because it was believed that the parallel postulate was a consequence of the earlier ones. So there was a lot of false proofs mathematically to try to establish that, but they really are independent. Okay, I love your question because once you assume the parallel postulate, de facto, what you just told me is the way to think about it. Alpha prime is beta plus gamma. So of course alpha prime is bigger, has a larger measure, has a greater measure than beta and gamma because it equals the sum of them, and both those measures are positive. Okay. 1 + 2 = 3. Okay. It's in that. Okay, but if you say you don't have the parallel postulate at the moment, and you say, is there anything else you can say without having to use the parallel postulate? And so I'll go back to the discussion. Why did I do it this way? Well, if you go back into the start here, the fact that if a pair of alternate interior angles are equal, then the lines are parallel, that does not depend on the parallel postulate. Logically, it can be established as true without appealing to that. It only needs the SAS axiom. The SAS axiom is what begets this exterior angle theorem. The converse direction needs the postulate. Okay. Okay. So there's something interesting going on here. And so I'm not pretending like, oh, yeah, I thought of this right after dinner last night. No, there's something going on. Okay. So let's go back to the picture. And say, how would I prove that alpha prime is greater than gamma? How would I argue that? And it's an argument that's much like the problem you just did in assignment 2. So here it goes. Construct the midpoint of A and C. Okay. I'm going to call that midpoint, say D, A, B, C, D. Construct the ray that begins at B and passes through D. Now, by the way, this is in the worksheet in the notes. So I'm just walking you through the worksheet. Okay, consider the circle that has D as a center that passes through the B point. What do you see about that circle? Well, it intersects that ray in a second point. If you were to describe that ray, what might be a nice way to describe it? Let's call that second point E. What's true about that second point? Well, it lies the same distance from D as B does. In fact, it's the diameter of that circle. Now, in the worksheet, I said, consider the triangle ADE. So consider the triangle AD and E. And compare it to the triangle CD and B. Okay, so let's take a look at them. So we have two triangles here. We've got the ADE triangle. And we've also got the CDB triangle. And is there anything you can tell me about those two triangles?
I mean, but I'm pretty sure
They're congruent. And guess what axiom holds? The SAS holds.
Oh, yeah.
Where do you think it holds? At what vertex? At vertex D.
Yeah,
Why does it hold at vertex D?
because we constructed those four segments to be the same way, or corresponding ones. So
Yeah, so notice D is the midpoint of A and C. So that means DA and DC are equal. Oh, but DE equals DB by the circle constraint. Now that the included angle is the angle at vertex D, and that's a pair of vertical angles. So our vertical angles theorem says vertical pairs are equal. So that means SAS. That means the two triangles are equal in measure. I mean, are congruent. So what does that mean about the angle DAE? What can you tell me about the measure of angle DAE at that point? DA and E has to be gamma.
So then obviously gamma is less than.
Well, yeah, so obviously it's less now than A prime because why? What do you notice? Well, you notice that DAE plus EA something, this unnamed point here, they add up to alpha prime. And so both of them are positive, which means alpha prime has to be greater than gamma. So no parallel postulate required. Now, by an analogous argument, you would show alpha prime greater than beta. In fact, I would encourage you to set that argument up. It's not hard. It's just tilting your head. Okay. All right. We're at 12:52. I'll have office hours. I might be a little late to my office hours tomorrow, but I encourage you to get in touch with me during the week so that you feel like you're making progress and it's not midnight Thursday when you're thinking about it. I'm asleep at that time. I'm an old guy. Okay. Yeah.
So how do we know the angle's the same again?
Because once I've established, you mean the ones at vertex D?
Yes.
That's the vertical angle theorem. Anytime I have two lines that are intersecting, they form two pairs of vertical angles. And the theorem is that each of those pairs is equal in measure.
essentially, it's a consequence of the supplementary angle.
Right. It's two ways to add up to 180.
Yep. Because if A plus B is 180 and B plus C equals 180, then A equals C.
Right. That's right. Okay, good. I will see everyone and thanks for showing up and participating.